Good morning.
Slowing down. It's a little bit of a smile. Or you.
Mhm. Let's get started. Oh no. Morning. Okay, well, looks like it's just you and me. So let me share my screen and we'll talk about okay. Okay. Hey, Eve. We used to meet like this before, didn't we? Anyway, let me go to where we need to be. We're going to start by showing you around what I've done here. Okay, so we have the lectures, of course, if you need that at all. And then we have the PowerPoint that we're going to be using, which is known as Lewis structures. And then after that, why is my video? My video's not here. Oh no. No, there it is. There's the video. Never mind. I was like, I'm blind. I didn't see it for a minute. Okay, so Lewis structures. I hope everybody else can join. Like I said, pay no mind to those pages because they're wrong. I need to take those off. Read the chapter. It's no longer chapter 6. It's another chapter, but because it's a different book. But the main thing to remember here is that we're talking about the octet rule that we learned. Now, the octet rule just states that when elements form bonds, they want to have 8 electrons. And that's kind of what they do, except for the first 3 groups. And hydrogen, of course. Hydrogen, if you recall, hydrogen only has, one layer, right, of electrons, one level. And that means that by design, the first level can only have 2. Therefore, hydrogen can only have 2, which makes sense. The other ones that are exceptions to that rule are groups 1, 2, and 3, which do not, when you look at the central atom, they don't really need 8 electrons around them. They're happy with just 2, 4, or 6. Now, the one that has 2 can never be a central atom, but the one that has 4 or 6 can. And then you have what is known as an expanded octet. And that is when you have more than 8 electrons. And those are really, they're giving you some examples here, but really all the elements on from row 3 down on the periodic table on the metalloid side would qualify as anybody that can get an expanded octet. Okay. And sulfur right here, as you can see, has 6 bonds, which means you have 12 electrons around sulfur in this case. And we'll look at that, you know, slowly after we do this. And then there's these things called radicals, which have a weird odd number of electrons. But those are very unstable and they don't last very long. But just so that you're aware that they do exist. All right, so here's the one picture that you want to take today, or notes, whatever. Number one, you have to find these are the steps on how to draw a Lewis structure. Now I'm going to give you these. I'm going to give you another one in the video, but this is the first one that I'm going to do. This is how I learned it. Okay. And then there's a second way that the girl on the video will teach you. And then there's yet another way that I do. So up to you which one you use. So finding the total number of valence electrons is, how do we do that? Well, we look at the periodic table and the group number tells me how many. So if you're looking at carbon, for example, you have 4. If you're looking at oxygen, you have 6, and so on and so forth. Okay, that's how we do that. And then you multiply that number by the number of atoms that are present of that kind. And the next thing is you arrange the atoms so that the singular atom is usually in the middle. And if you can have more than one possibility, you can have, you will know which one it is because it's the least electronegative. And we're not talking about hydrogen because hydrogen could never be in the middle because it only can make one bond, right? But any element that can make 2 bonds or more can be in the middle, okay? Then you will form bonds between atoms. That means draw a line. Then you will take the rest of the electrons from the pile. So basically, let's say you had 24, you made 4 bonds, you subtract 8 from that, okay? So the 8 gives you, 24 minus 8 gives you 4, right? No, 24 minus 8 is not 4, 14. I meant to say. And then you know to distribute those electrons among the others. And we will be applying this. And if there are not enough electrons on your count that you did on number 1, right, to go around, then you form either double or triple bonds. Okay, so let's apply this. Here goes. CF14, carbon tetrafluoride. Number 1 thing is to do the electron count. So we have 1 carbon, right? There's only 1 because there's nothing, no subscript afterwards. So 1 carbon, and carbon, if you look at the periodic table, it has 4 electrons. So we got 4 electrons from carbon. Then we have 4 fluorines because that 4 right here indicates, let me see, let me keep. No, I don't want annotations. I want the spotlight. Yeah, right there. No, spotlight. Okay, right there. See it? All right, that one is telling me that I have 4 of those. So 4. And that gives me 28 of those. So adding them together, you get 32. Okay, that's step 1. Step 2 is to place the one that looks like the central atom in the center. In this case, it would be carbon, and it's also the least electronegative, so we know that is correct. And then it's said to make bonds towards right? All right, so we used bonds. That means we used electrons out of that total already. We used 8 of them because each bond takes 2 electrons. So we're subtracting those from the total. Now we have 24 electrons left. And the last thing it said was to distribute them among the outer atoms that need 8. And there you go. Now, let's look at this diagram because it'll be a little bit confusing if I don't explain something. All right, when you look at fluorine, okay, right here, that right there is 8 electrons if you count, because you got 2 from the bond, 4, 6, 8, right? That's 8 electrons total. All right. Let me clear that. Undo those 3 little checks. Okay. So every one of these is satisfied. It's an octet, right? So far, every one of these fluorines. What about carbon? Well, let's look at carbon. Let's do a different color. Let's do red for carbon. Carbon actually has these electrons around itself. You see that? And that means you have 2, 4, 6, 8 electrons around carbon also. So we're good. So this is it. We're done. We have finished the Lewis structure. Now, let's go to another one. Let's do beryllium chloride. All right, so beryllium has 2 electrons, and there's 1 of them. Chlorine has 7, and there's 2 of them. So a total becomes 16. All right, now, who is the central atom? Well, beryllium is. Beryllium is the one that we only have 1 of, number 1. And number 2, it is the least electronegative of the 2. So yes, we make bonds. We subtract the number of bonds, which in this case, the number of electrons that we used in the bonds, which is 4. And then we end up with 12. Now, 12 electrons is enough to go. And we always put the electrons around the chlorines or the atoms that are not in the middle first. All right, and that gives us 12. And then you're looking at beryllium. Beryllium says, beryllium's not full. But remember, beryllium is an exception. So let's remember that. Beryllium, let me put it in black. Yeah, beryllium is in group 2. So it is an exception and only needs 4 electrons for valence. Let's just say 4 valence electrons. Valence means outer, right? So we just know that. Okay, and that's what we want to know. So now, knowing what we know, we can say beryllium's happy because beryllium has 2, 4. And that's what it says here. So it only needs 4, beryllium's fine. Chlorine, 2, 4, 6, 8 on both sides. They're happy. So we're done. And the other thing that you always want to do, and this is kind of like a proof. Remember, we started with 16. So if we use more than 16 electrons, our structure is wrong. But if you count them, you got 2, 4. Let's see, let me do the spotlight so that we can see where I'm going. 2, 4, 6, 8. And then the other side, 2, 4, 6, 8. 8 and 8 is 16, which is what we started with. All right. So yeah, that is definitely a good thing. All right. So let's keep going. And I'm going to erase that. All right, now carbon dioxide. Let's look at this one. Carbon is in group 4. We have 4 electrons for it. Oxygen is in group 6. So there are 2 oxygens, so 2 times 6 is 12. We add them, that gives us 16. We make our little middle, and that looks good. So we have used 4 electrons, and we subtract them from the total. Now, we have 12 electrons left. Here's where we do it. Okay, so we just place them around the atoms. Sorry, the atoms that are there. Now, carbon is not in group 4. I mean, is in group 4. It's not in group 2 or 3, so it's not an exception. Carbon needs 8 electrons around it. You don't see 8 here, do we? So what we do is we take these electrons and we move them here to make a bond, okay? And that is when we're forming a double bond. So we have 2 double bonds for carbon. And watch what happens. See? They moved. All right, so let's clear that. And there's the proper structure. Now remember we said that if we ended up with more electrons, we did it wrong. So let's count. 2, 4, 6, 8, and the other side is exactly the same. So 8 and 8 is 16, and that's how many we started with. So we are good. All right, next. Another strange thing that can happen is we can have a polyatomic ion. Polyatomic ions have charges. When you have a charge, there's a little bit of a different thing to do. You do the same count just like you did before, except if you have a negative, you add 1 electron for each negative charge. And if you have a positive, you subtract 1. Simple, from the total. All right. And then the last thing that you must do, or you will get it wrong, is to place brackets around the ion and label the charge. Okay, so what does that say? Let's look at this one. ClO4. All right, same exact process. 1 chlorine, group 7, 7 electrons. 4 oxygens, group 6, 24 electrons. Add them together, you get 31. Remember what we talked about? We don't like odd numbers when we're doing this because they're all electron pairs. That's when this extra electron right here is added because we have an extra one. And that's what the chart is telling us. So now we have 32 total. Now that makes more sense. Now, we know that chlorine is the least electronegative of these, but we also only have 1 chlorine, so it's obvious that it's going to go in the middle. Then we make bonds. That's 8 electrons. We subtract that. We have 24 electrons that go around the chlorine, so which is pretty good because we already have 2 that are being shared between, I said the chlorine, I meant the oxygen, 2 that are being shared between the chlorine and the oxygen. So we only need 6 more, and 6 times 4 is 24, which is all we have left, you see? Now, this would not be a correct Lewis structure as is because we didn't do the last step, which is to put it in brackets and label the charge. You see that? Okay. All right. Next one, we have a positive one. Okay, so same thing. 1 nitrogen times 5 because nitrogen is in group 5, and 4 hydrogens times 1. That gives me a total of 9. 9 electrons is an odd number again, but we have a positive charge, which means we need to subtract an electron. We get 8. So we need to do our little sketch, crude sketch, which is what we're doing now. We put the bonds. The bonds used 8 electrons. We have 0 left. And that's exactly right because hydrogen is happy with 2, remember? So we are good. Now, would this be a correct structure? No. Why not? This. If you forget to do that, your structure is wrong. As long as you have a positive or a negative here, you must put it here when you finish. Because if I see this, I would know something was wrong, because nitrogen can only have NH3. So to be not, you'll see. We're going to look at next one. All right, so now there's this thing called resonance. What is resonance? Resonance is the many structures that represent one single molecule. What does that mean again? Well, that means that you can have a double bond that can move around. So if you have a double bond that can move around, you have to represent every single one of the structures. So if it can move around, it can be on the top, on the bottom, or on the side, the left or the right, whatever, then you've got to move it around and show how many possibilities you actually have, so that people understand that this is not one structure, but three, or not one structure, but two, or so on and so forth. All right, so an example of it would be the O3 or ozone. If you look over here, I know it looks the same to you, and if you flipped it, it actually would be exactly the same. Like if you turned it 180 degrees, it would be exactly the same. But the main thing here is that the double bond on one is on the left and on the second one is on the right. And there's a double-headed arrow. What does that mean? That double-headed arrow just means that it can go constantly changing like this, back and forth, back and forth, back and forth. So we want to remember that by putting a double-headed arrow, which means it can go both ways, right? It doesn't just go one way. All right, so let's do this one. And I know that you can see the background, which it's okay, but we're going to do the math for the whole entire thing. All right, I'm going to use, let me use white, because white's better for this. I said white. There we go. All right, so we have one sulfur, right? And there is one of them, and sulfur is in group 6. So that gives us 6. We have 3 oxygens, also in group 6. So that gives us 18, correct? Which is a total of 24. Okay, now we are going to do what we have been told to do, which is put the sulfur in the middle and then put 3 oxygens around it. And yes, I know I'm skipping one of the steps, which just you put them around, then you make the bonds. I did it all in once, which is fine. All right, so we have 2, 4, 6 electrons that we used in the bond, right? Now we subtract that from here and we get a total of 18, right? So 18 electrons, I'm going to place them around my atoms. Okay, I've run out. I have used 18 electrons, and sulfur is going, wait a minute, I am not a happy camper because I do not have 8 electrons around me. So what we do need to do is we need to erase one of them and put it in the middle. There you go. Now that's the official structure. But couldn't that double bond also have been put here, right? And then of course we would need to adjust and then erase these, right? Right? Or it could have been put to the right. So once again, we can say, oh, well, no, that's not exactly right, but it actually is right. It's not wrong. It's just not exactly right, like we said. So what we're going to do is we're going to return those big old things. And then we're going to erase another set. We're going to erase this one. And now we're going to put, and you notice that I'm erasing as I go because, oops, what in the world? I don't want an arrow. Undo that. I need that. Okay, there we go. And see, oops. Oh, well, it's fine. It needed to be skinnier, but that's all right. Undo that one. Come on, undo it. There. Now it will be. All right. So there you go. So that's how we represented all three structures. Now let's clear all this junk and redo. And we're going to watch how we would need to represent it. Notice there's no charge or anything. So we just would put it like this. See, it can easily go to the right or the left, or it can go on the top. So any of these three structures is correct. So in order for the structure to be correct, you must show every one of them. Okay. So that's that one. Let me show you the other. That's how I do. How I remember learning. Then after a while, I didn't even need to look at that, but that's just because I'm a chemistry person and we saw this a lot. But in your case, you're not. But here's a really good video that'll help you.
I'll be helping another YouTuber, Melissa Lucy, prepare for her next exam.
You might want to rewrite. You might want to write notes.
A free study plan that you can download using the link in the description. That study plan has several videos or other resources that
like I said, you may want to take notes while she's talking because her way is a little different than mine. Hers is only 3 steps. Okay.
Personally recommend for you. All right, let's learn how to draw Lewis structures properly. So today we're basically going to be focusing on how to draw Lewis structures. I know that there's like so many questions that you're thrown with like Lewis structures where they expect you to know one, how to draw it, and then the geometries, resonance, all of these other words that we're going to learn later on. But for now, let's at least get a good foundation of just understanding how to actually draw the structure, because that's I'd say that's the most important part, because if you don't have that right, then everything else is wrong. So no pressure, but let's focus on just understanding this. So we've talked about this before, looking at valence electrons. And I know I went over this a little bit where I was just talking about what isn't a valence electron. It's the electron that's on the outermost shell of an atom. And really what I want you to memorize is everything that is highlighted here. So just knowing that this group only has one valence electron. The next one has 2. We're not going to look at anything to do with transition metals for Lewis structures. And then the next one would just be, this column is going to be 3 valence electrons, 4, 5, 6, 7, 8. You get the point. But it's going to be really important to actually have these memorized. So some of the most common atoms that we're actually going to see that we're going to use, I'll just highlight them real quick. So definitely hydrogen. That's going to be something that's really known. We're going to see that so much. Carbon is one of the most used atoms, I would say, that we're going to use for Lewis structures. Same goes with oxygen. Same goes with, let's see, nitrogen. And then we probably are going to see some fluorine, chlorine, sulfur, and pretty much a lot of just the nonmetals. Because the whole concept here with Lewis structures is the ones that we typically see are covalent Lewis structures, meaning they share electrons, and it's all nonmetals. All right, so if we remember that concept, like going from ionic compounds to covalent compounds, ionic compounds consist of one metal and one nonmetal, and then they're actually transferring electrons, versus covalent compounds, which are sharing electrons, and they also consist of just nonmetals. Okay, so I think we're okay with that. Let's just start off with all the different steps of how to draw a Lewis structure. So first things first, we're going to have to know every single valence electron. So like carbon has how many valence electrons, and then same with hydrogen. And then we're going to add all of that together. So kind of going back from memory, or you can look at your periodic table, how many valence electrons does carbon have?
Carbon has 4.
Cool. I'm going to write it up here. So carbon has 4. How many valence electrons does hydrogen have?
1.
Perfect. And then we would multiply this by 4 because this subscript is telling us that there are 4 hydrogens in the structure. So that would give us 1 times 4, so 4. And the next thing is just to add everything together. So I would add just 4 plus 4 to give us 8 valence electrons. So first step is done. All I have to do is calculate the total number of valence electrons. We said it was 8. The next thing is identifying which one is going to be the central atom. So for the central atom, I know this one's kind of like obvious because there's 4 hydrogens, so that has to surround the carbon. But just to note, carbon will typically always be, or actually it will always be the central atom if it is in the structure. Okay, so carbon, number 1, that's always going to be in the center. Now, if there wasn't carbon in the Lewis structure, then it's going to be the least electronegative. So the least electronegative atom would be your central atom if carbon isn't there. Okay, so it doesn't apply for this case because hydrogen is never, and also that's actually something to note, hydrogen will never be your central atom because it could only have 1 valence electron, meaning it's only going to be able to create 1 bond. Is this making sense so far? I know I'm like throwing a lot at you. So
Yeah, but when you say least electronegative, like if we were comparing 2 and we're following that trend, then the one opposite of the trend, is that what you're saying when
Yes,
you say least?
correct.
Or okay.
Correct. Like if I were to have something like, I don't know, like this, and then you were asked like, oh, what's the central atom? And I know they're not going to be given this exactly, but we'll do an example. But from there, you would say, okay, which one is the least electronegative compared to chlorine and fluorine? Well, that would be chlorine. So chlorine would be your central atom. Does that make sense?
Oh, yes, because it goes up and to the right,
Yes,
like on the periodic
right.
table. Okay,
Right.
cool, got it.
But we'll see an example of that. For now, I just want you to kind of start to understand the steps. So choosing our central atom, that's going to be carbon. So, okay, I'll put that right in the middle. Next, it's going to be surrounded by 4 different hydrogens. So I'll put a hydrogen, hydrogen, and a hydrogen. So that's done. Step 3, I do this a little bit differently. So at first, you're going to learn like the Lewis dot diagram where you'd see like, oh, carbon, we said has 4 valence electrons. So you're going to draw it this way if it's just on its own. And then hydrogen only has 1. So it could only make 1 bond. So these would combine together to then form 1 bond. So it would look something like that. And then you'd still kind of see that whole approach here. Like if I were to actually put, to show you this, that's carbon's Lewis dot diagram. I would do the same thing. I'm going to do this in blue for hydrogen. So just 1 valence electron, 1 valence electron, same thing here, same thing here. Essentially what's happening is they're going to form a bond because 2 electrons form a single bond. So instead of doing that each time, because it's time consuming, what I typically would just do is simply put a single bond already there, because this is telling us that they're going to bond regardless. Okay, but does that make sense? What I'm explaining there?
Yes, like the line.
Yes, yeah. So, and it's just because like we're basically connecting the dots here, so it's going to form a single bond either way. So it kind of just saves you the step of drawing the Lewis dot diagram and then, connecting everything. I kind of like want you to understand that they're going to form a bond regardless. So that's, that would be the next step. And then from there, the very last thing, part of step 3 is to just make sure that all of the electrons add up to what we did in step 1. So in step 1, we said that there are 8 total valence electrons, and we want to double check that that's true. So if I were to, I'm going to draw this in red. If I were to kind of recount these electrons, I would see, well, remember, 1 bond consists of 2 electrons. So there's 2 so far. So 2, 4, 6, and 8. So yes, that checks out. And because that's correct, because that checks out, we're done. That is the correct Lewis structure. So those are, I'd say, like the main 3 steps for a typical Lewis structure. That's what we would apply. Questions here?
No, that makes sense.
Perfect. Moving on to the octet rule. So we just drew our structure, and if we saw there was 8 valence electrons. That's what we said. So this actually follows the octet rule. And what the octet rule is saying is that the central atom prefers to have 8 valence electrons surrounding it. Like it's stable, it's happy. And we always want to make that central atom happy. So we can look at this again, and I'm just looking at the central atom, so carbon, and I'm seeing that there's 2 valence electrons here, so 2, 4, again, 6, and 8. Because there are 8 valence electrons surrounding that carbon, then I know, yep, this follows the octet rule. It's stable, it's happy. Once again, the structure is correct. So I'm going to keep applying this. Okay, I'm going to keep applying one, the octet rule, and the steps that we went through to draw a Lewis structure. So once again, let's just start with the first part where we're calculating the total number of valence electrons. How many valence electrons does phosphorus have?
5.
Yes. What about chlorine?
7.
Good. And then we'd multiply by 3 because there are 3 chlorines. So 21. We'd add these together. So 5 plus 21 is 26 electrons. So check. Next, we have to choose our central atom. What would be our central atom in this case?
Phosphorus.
Yes. And then another way too, when I said like, oh, the least electronegative atom is going to be your central atom, that will help you a lot when you have like larger structures. So like when there's typically like more than one central atom, which we'll go over, but that's something that we're going to see. For this case, we could have just seen that phosphorus is by itself, and the fact that there is a 3 subscript, that tells us that there's going to be 3 chlorine surrounding the phosphorus.
Oh yeah, so you can just look at it now.
Yeah, right.
Okay, that makes sense.
So our central is phosphorus. And then next, I'm just going to place a bond. So I said that there's 3 chlorine surrounding phosphorus. And then I'm already going to say, hey, this is going to add up. So there's a bond here, bond here. Now, I also want to talk about the different lone pairs. So lone pairs just mean that these are lone pairs. They're electrons that are not like on a bond. So they're still on that atom, but they're not actually within a bond. So let me show you this again. Just in the very beginning, I will draw the actual like Lewis dot structure. So for chlorine, we said there are 7 valence electrons. So I'll say there's 1, 2, 3, 4, 5, 6, and 7. And I would do the same thing for every single one. Now, if we realize there's always going to be one here that's being shared with whatever element it's bonded to. And then there's going to be 2 electrons on every single side, essentially. So there's going to be 6 electrons, or 6 electrons, 3 lone pairs, if that makes sense. Like these are lone pairs. These are the 3 lone pairs on the chlorine. This making sense so far?
Mm-hmm.
Okay, cool. And I would basically do this all throughout for every single one, just showing you that there are 7 valence electrons on that chlorine. And then now I would look and see, okay, well, does phosphorus have 5 valence electrons? Well, no, it doesn't, because here's 1, 2, 3. Now I need a lone pair, 5. So I could have seen it that way, or I could have done what I prefer to do, which is kind of like the faster way. So the faster way of doing this, and I'll show you again, is just to simply start with drawing the bond. Then from there, I see, well, actually from there, I'm going to actually draw the lone pairs on chlorine. And then something to note, every single, basically any single like halogen, same with our oxygen, sulfur, and so on, those are going to also have like lone pairs like this. You're going to see a pattern. So typically I'm pretty much just going to say for our halogens, you're going to constantly see a pattern with this where there's going to be 3 different lone pairs on that atom. So that's why I already knew that, okay, I just have to put all the lone pairs in, put a bond, and I'm almost done. The last step is then to know that, well, 1, this has to follow the octet rule, and it doesn't right now because there's only 1, 2, 3, 4, 5, 6 valence electrons on our central atom. It wants to have 8, so I add 2 more on phosphorus. Another thing I could have done to also check this, which is the end part, is seeing if all of the electrons add up. So I can just count this again. So I can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, I could do that if I truly wanted to. Or I could also do this, go a little bit faster here and just saying that this is 8 valence electrons. There's 3 here. So 3 times 8 gives us 24, plus the additional 2 here. I know there's so many things that I'm throwing, but this is essentially the concept of drawing Lewis structures.
Yeah, no, that makes sense.
Perfect. Okay, you get the point. And it looks something like this. I just want to leave it. Cool. Moving on. All right, so we saw that we can put lone pairs on the central atom. And then now we're going to go into just the different types of bonds. So just recall that when 2 electrons combine, that forms a single bond. When 4 electrons combine, that forms a double bond. And then when 6 electrons combine, that forms a triple bond. So I'm going to do the same sort of concept here again. Let's just identify the total number of valence electrons. So I'll start with carbon. How many are there?
There are 4.
Good. What about oxygen?
6.
Perfect. And I'll multiply this by 2, giving us 12. So 4 plus 12 gives us 16 electrons. And then what's our central atom?
Carbon.
Yeah. And that's surrounded by 2 oxygens. And then again, I'm just going to place the bonds already there. So I did all this so far. Now I'm just placing a bond and a bond. And then I also know that oxygen is going to have these electrons surrounding it. Okay, these lone pairs. So if we notice, carbon isn't happy, okay, because it doesn't have a full octet. So it doesn't have 8 valence electrons surrounding it. So far, there's only 1, 2, 3, and 4. So what we have to do is we actually have to form a larger bond or a double bond. So how we do that is by actually moving electrons to then give us that double bond. So we're not adding an additional amount of electrons because this has to give us 16. And if we notice, this already has 16. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yep, I can't add any more electrons to that central atom. So instead, I have to form a double bond. And when I do this, I'm essentially taking these electrons and moving it to form that double bond. So there's no longer 3 lone pairs. There's now just 2.
Okay.
And then this is something else to note, is that if this were something that was just bonded to something that was single bonded to an atom, then I would have 3 lone pairs. If this was double bonded, I would just have 2 lone pairs. If this was triple bonded, I would just have 1 lone pair.
Okay. Yeah.
So definitely be aware of that, just because I have seen this where you add too many electrons or too many lone pairs, and you do get the answer wrong, unfortunately.
Okay.
So, okay, perfect. And then we can check again and just see, yes, this does obey the octet rule, because here's 1, 2, 3, 4, 5, 6, 7, and 8. That's happy. And then we didn't add any additional electrons. It's still 16. All right, this is another one that's a little bit larger, I'd say.
Sorry.
So for this one, we're going to have multiple central atoms. And how I would approach this is just by seeing, well, there are several hydrogens, right? There's 4 hydrogens in this structure, but our central atom could never be hydrogen, since that could only form 1 bond, since it only has 1 valence electron. So our central atoms can only be carbon and oxygen. before I do that, I have to figure out how many valence electrons there are in total. So carbon has how many valence electrons?
4.
Good. What about oxygen?
6.
Perfect. And then and then hydrogen we know has 1. There's, don't forget about actually counting them all. So this is 3 plus an additional 1 at the end. So there are 4 hydrogens. 1 times 4 is 4. We'll add everything up. 4 plus 6 plus 4 gives us 14 electrons. And then we said that our carbon and our oxygen were our central atoms. So I'm going to draw it this way. Now, if you were curious and you weren't sure, how do I draw this? Like, how do I know where the hydrogens go? Like, what does it bond to? Well, this is typically written in the form that it wants you to draw the structure. So this already is telling us that there are 3 hydrogens on this carbon. So I would surround this as follows, and then same goes for the next one. This is already telling me, oh, that OH, that H is going to be together. So that's how I would put a bond for everything. And I'm not done yet. So then I would then look at the octet rule and see, is carbon happy? Does it have 8 valence electrons on the central atom? And I would see that, yes, it does, because here's 1, 2, 3, 4, 5, 6, 7, 8. That checks out. Our other central atom is oxygen. And now that has to also have 8 valence electrons following the octet rule. And it does not, because this only has 1, 2, 3, and 4. So instead, we would have a lone pair, 2 lone pairs actually, to give us 8 valence electrons. Now this is complete. Questions?
No, that makes sense.
Perfect. Next one. Okay. So with this one was actually on one of your slides or in class assignments. And just a note, they did give you a hint. They did tell you that the oxygen was bonded to this carbon. So just a note, because I know I just said for the last one that they typically will give you, like this is already written out the way you should bond it to. Like these hydrogens go with this carbon, this hydrogen goes with this oxygen. So this one actually had to tell you that this oxygen goes with this carbon. Yeah,
Okay.
That's not just like, you're magically gonna know. No, they would have to explain that. So once again, let's just calculate how many valence electrons we have. So I know you know this by now, but you're gonna see this a lot. These are probably the most common atoms that we're gonna see are carbon, hydrogen, and oxygen. Carbon we said has 4. There are 2 carbons in this case, so 8. And then for hydrogens here, there's 3 here plus this additional 1. So there's 1 valence electron times the 4 hydrogens, so 4. And then there's only 1 oxygen, so 6. So I would add this all together. So 8 plus 4 plus 6 gives us 18 valence electrons. And then now looking at this, what's our central atoms? So we're gonna have two central atoms. What do you think are the central atoms?
So carbon is one of them.
Good.
Can we have carbon again?
Yes, we can. Perfect. Yes, we can.
Okay.
And if you were trying to, actually, this goes back to the rule I was talking about, where if I'm trying to decide if carbon or oxygen is like the other central atom, we would say, well, which one is the least electronegative? Oxygen is the most electronegative. Carbon is the least electronegative. So I know that the other carbon also will be our central atom.
Okay.
Perfect. And then next, I'm just going to see that these hydrogens go to that carbon. So I'll place them around that carbon. This originally told us that this oxygen will be bonded to that carbon. So I'm just going to put that on top. And then I'll put the hydrogen next to the carbon. And then once again, I'm just going to build this just by adding single bonds all throughout. Okay. And then from there, I'm just going to double check if we have 18 valence electrons and if this obeys the octet rule. So for carbon, this does obey the octet rule because this has 2, 4, 6, and 8 valence electrons. Next, for this carbon, it does not because this only has 2, 4, and 6 valence electrons. So what I would need to do, and something to note, was just remember this oxygen has 3 lone pairs. So if carbon isn't happy, meaning it doesn't have 8 valence electrons, it's not following the octet rule, it wants to have a greater bond, so it wants to have a double bond. So I would just move one of these electrons here to form that double bond.
Okay.
And now this is complete.
So
Yeah.
would it be wrong if you just decided to add a lone pair to the carbon itself?
Yes. Yes, it would.
Why?
Because here.
Oh, then we're
Because-
adding electrons.
Yes, exactly. Then we have 20 valence electrons. Exactly. So you always want to have the total number of valence electrons. That's why that's the first step. And then another thing, like, yeah, that's actually like the main reason. We always want to just kind of like, we're moving around the electrons just to get the best structure. Like that's essentially what Lewis structures are. Like we're just trying to build the best, most favorable structure.
Okay.
Cool. And there's exceptions, of course.
Oh my God.
So I know, but luckily these aren't that terrible. Okay, there's going to be 2 main exceptions to the octet rule. So we could have an incomplete octet, meaning there's going to be less than 8 valence electrons on the central atom. And I'll tell you how you can just easily tell. So the ones that will have an incomplete octet are basically going to be the atoms that don't have 4 valence electrons to begin with. So remember, carbon has 4 valence electrons. These had 3, these had 2. So what I'm looking at is I'm literally just looking at the groups that do not have 4 valence electrons. And the reason why I just highlighted boron and beryllium is because those are the most common ones. So those are typically the exceptions to the octet rule that you will see. That's pretty much it. So I literally would say those are the main ones that they always use. But just knowing that they're always going to have less than 4 valence electrons to begin with. That's how you know it's going to be an incomplete octet.
Okay.
And I'll show you an example. So how many valence electrons does boron have?
3.
Good. What about fluorine?
7.
Perfect. So 7, I'm going to multiply this by 3 because there's 3 of them. So 3 plus 21, that gives us 24 electrons. What's our central atom?
Boron.
Perfect. I'm going to surround this by 3 fluorines, putting our single bonds already, putting the lone pairs, knowing that halogens will always have those 3 lone pairs. And then now I'm just going to double check that I do have 24 electrons. So how I could easily do this is just by seeing that this is 2, 4, 6, 8. So this is 8. This is also 8. 8 times 3 does give us 24. So that checks out. But I know that this is an incomplete octet because there's only 2, 4, and 6 valence electrons on that central atom. But it's happy. It's totally fine. So we would just leave it like that. That is the best structure. That is the correct structure.
Okay, so the exception meaning that I get what you're saying, so it's less. Okay, cool.
Yes, exactly. And then the other one is the opposite way. There's more. So it's an expanded octet. There's more than 8 valence electrons on the central atom. And I'll explain what that would be. So the place that it's going to actually start is going to be the 3rd row. So this is the 3rd row, but specifically, it's going to be here. So the 3rd row, and then below. So in your book, it's probably going to say the 3rd row and above. And though that's correct, mentally, that doesn't make sense because this is row 3, right? And we're thinking, oh, if this is row 3, it would be above it, right? 3 and above. And that's not how you're going to think about it, right? So I like to think about it as it's row 3, and like physically below
That makes
everything
way
else.
more sense, yeah. Because I would totally be thinking that. But are they saying
Right.
that because like based on the energy, like the energy levels of being like 3,
Yes,
4, 5?
correct.
Oh, okay. That makes sense.
Exactly. That's how they're basing it. Yeah. So, but I just prefer to kind of box it up and say, these are the main ones. Just know that these are your exceptions. So I typically say, yeah, 3 and physically on the periodic table below, you know. So the main ones that I always see, and I wrote that down. So the examples that you're probably always going to see are phosphorus. Let's see, all of these, hold on. And sulfur is one of them as well. These are probably the most common ones that are going to be used. Now, something that I want to make a point here. These all have the possibility or potential to form an expanded octet. It doesn't mean that every single time they will. And I'm going to highlight back to one of the ones we just did. So phosphorus has the potential to form an expanded octet if it needs to. But as we saw previously with this example, it didn't have to, right? This had already, 2, 4, 6, 8. This obeyed the octet rule, and that was fine. However, if I needed to add, like if there was 5 chlorines, then I would see, okay, this does have that possibility of having that expanded octet if it so needed to. So it's based on whatever atoms are attached to it.
Okay.
Okay, we'll do some examples there. Versus, like, let's say boron or beryllium, they're always going to be incomplete. Like, it's not saying that they have the possibility. No, those for sure are incomplete. They're not going to obey the octet rule. So here's an example for an expanded octet rule. So let's just look at how many valence electrons we have again. So for xenon, how many valence electrons does that have?
It has 8.
Good. What about fluorine?
7.
Perfect. Good, and then we'd add these together. So, and I just found the 4 from here. So 28 plus 8, that would give us 36 electrons. Okay, what's our central atom?
Xenon.
Good. We know this is going to be surrounded by 4 fluorines, so I could draw it like this for now. I'll put our single bonds. And then, of course, any sort of halogen is going to have 3 lone pairs. So just putting them all. Perfect. And then we're going to count and see, does this have 36 electrons? So this has 8, right? 2, 4, 6, 8. That's 8 times 4 of them. So 8 times 4 gives us 32. We need more. So this right now only has 32 valence electrons. We need 36. So because of that, we need to add 4 electrons. So that means we're going to add 2 lone pairs on the central atom. So that's something to note, is whenever you basically put all of the electrons on the elements that are like surrounding it or on the outside, and if you don't have enough valence electrons, then you come back to the central atom and add more.
Okay.
And that's how, in this case, we do have 36. We will see that this is going to be an expanded octet because this has 2, 4, 6, 8, 10, and then 12. So this actually has 12 valence electrons surrounding it, but that's completely fine because it is part of the exception right here.
Okay.
And we're going to keep going, and we're going to see Lewis structures of ions. So now we're adding a charge. So this is basically going to be the same sort of concept where, remember that cations, we're actually going to lose an electron, meaning we're going to subtract an electron, and then anions, the negative charge, we're actually going to add an electron. So we're gonna add. So in this case, since we have that positive charge or a cation, we're actually going to have to subtract 1 electron at the end. So the first thing we're going to do is just identify how many valence electrons do we have. So how many are there for nitrogen?
There are 5 for nitrogen and 1 for hydrogen. We're multiplied by 4 though, so there's 4.
Good. So 5 plus 4, and then we would subtract 1 based on this one +1 charge, so subtract 1. And then instead of having, let's see, instead of having 9, we're actually going to have 8. And then that's something to also note, you're not going to be having like an odd number of valence electrons, because that would mean that we wouldn't have a pair, like a lone pair. So if you were to see that, there's, I'd say double check. Most likely there is a charge that you're forgetting to apply. So that's why in this case, we had to have this charge to reduce that number from 9 to an actual even number of 8. What is our, actually we're here. What's the central atom?
Nitrogen.
Good. I'm going to surround that by 4 hydrogens, placing a single bond all throughout. And then I'm just going to double check if this gives us what we wanted. So let's see, this is 8. So 2, 4, 6, 8. Yep, that checks out. The last thing, so the only difference now is that we have to actually place the entire structure in brackets and place the charge on top. This is whenever it's a charged or an ion, essentially. Whenever this is an ion, you have to put the Lewis structure in brackets and put the charge on the outside. It would be marked wrong if you didn't.
Okay.
We'll do the same thing for this next one. So now we have an anion, and I know that I'm actually going to add an electron. So go ahead and let's figure out again how many valence electrons we have. So how many valence electrons for chlorine?
Chlorine has 7 and oxygen has 6.
Good. And then multiply that by 4. Okay. And then I'm going to add 1 more electron. So 7 plus 24 plus this 1. Let's see, what does that give us? So this gives us 8. 24 plus 8. 32.
Okay. I'm glad you're not asking me to do that. I can't do quick math. I need my calculator for that simple stuff.
But I'll have you do, I'm going to have you do practice problems after, but that's fine. You can use your calculator to calculate it. That's not a problem. So what's our central atom in this case?
Chlorine.
Yes. Perfect. And then we're just going to place oxygen surrounding it and placing our bonds. Now the oxygen is going to have 3 lone pairs all throughout. And then we'll double check the amount of electrons. So in this case, I have, again, this is 8. 8 times 4 does give us 32. That checks out. The last step is to just place this in brackets and then our charge on the outside. So perfect. Keep practicing those steps to drawing Lewis structures that we covered. Take notes and really just give this all you got, because we're kind of in the middle of the semester right now. And you know what? I know you can do this. I know you don't want to repeat this class. And quite frankly, you're capable of doing this. And
All right. So that's how you do Lewis structures for every kind. Now you've seen more than one method. Come on. There you go. Sorry. I cannot go back to my meeting control. I'm trying. Anyway. So we went to this video, right? And that's what we were looking at. All right. So the 3 easy steps. I don't know about it's so easy, but they're the same. We just have more. It's the same steps. We just do it a little different. And the one thing that we want to know is that we know how to do it. So in order to do that, we're going to do a couple of these. And we're going to go ahead and someday it'll come up. Okay, there we go. I'm going to go ahead and make it a little bit bigger so you can see it, because otherwise you can't see it. Come on, there we go. You notice there is an answer sheet, which is just practice. So in your case, you don't need to, but the very first thing to do is to do what we know we need to do, which is the totaling. All right, so we have 1, Not one white and one black. Okay, so we have one phosphorus, right? And phosphorus is in which group? Group 5. So that's 5 for that one. And then we have bromines. We have 3 of them, and they are because of this, right? Remember, that's the 3 in group 7. So that gives us 21. We add these, we get 26. All right, now of those, which one would be the central atom? Like I said, it's usually pretty obvious because you have less of them. In this case is the phosphorus, and it is also the least electronegative. So then, well, I tend to do this backwards from her, but we do the bromines, right? And then we do the lines to it. Okay, so then we know that we have to, without a doubt, put some, and I'm making them big so that you can see them. And it's very hard to make a dot with your fingers, so I'm trying to do it like this. And we already know that bromine wants to fulfill the octet rule, just like she did, right? And we would see, normally this would be where we would have said, this is how I do it, okay? And see, this to me makes more sense, but she had a little bit of difference. Okay, so here I would have subtracted those 6 that I used from the bonds, right? And I would have gotten 20. So you notice I just used 18, right? Because 6 times 3 is 18. But I still have 2 more. And she always says, when you run out, put them in the central atom. And there you go. That is the correct structure for phosphorus tribromine. Okay. Tribromide, sorry, did I say bean? Oh my God. Sorry, I meant bromide. Yeah, okay, so there you go. That is your first Lewis structure. And that is correct. Now, if you would have done it like she did it, you can still come up with the same number because you would have counted all the ones that you had used, and then you would have noticed that you still had 2 more. So it would have been either way. And you would have checked each octet, right? And you would have known that phosphorus didn't have enough. So either way you do it, as long as you have the extra electrons, you can do it. But if you're short, remember, you got to do a double bond. Excuse me. All right, so let's clear these. And let's go to the next one. The next one is N2H2. Remember what she said? She said that they're usually drawn the way that they want you to do them, but we still got to do the math. Okay, so we have 2 nitrogens, right? And that's 5 of them per nitrogen. And we have 2 hydrogens with 1. So that gives me a total of 12 valence electrons. Normally, we know that we do not have, and she said, place them around. And, you know, that makes no sense to put it there. So let's take it off in there. We'll just put it where it really would make more sense for it to be. All right. We said that the nitrogen are going to be the central atom because hydrogen can never be. So the nitrogen gets a bond, bond, bond. Now, do we have octet rule fulfilled? No, we don't. So we need 1, 2, 3. Now, if we count, you can see that we've used more than 12. You see 2, 4, 6, and then you got 8, 10, 12, 14. So this can't be it. So we need to now undo those. And now let's see, 2, 4. So each one of these has 6, but actually 6 on this one and 4 more. So that's only 10. So something's missing. All right. You notice that we needed a pair somewhere in the middle here. How do we know we need a double bond? Because if we count them now, we have used 12. 4 from bonds, right? So 4 times 8 is 4 times 2 is 8, and then 4 more from being lone pairs. So 8 plus 4 is 12. So it checks. And that is the correct Lewis structure. Hydrogen does not need lone pairs. Remember that. Only nitrogen would. And nitrogen now has 4. 1, 2, 3, 4. 1, 2, 3, 4 each time, right? So we're good. All right. Also, she mentioned that whenever you have the structure given to you, it is meant to be written the way it's stated. Okay, so C and then O, and then you have 3 hydrogens that surround the carbon and 1 that surrounds the oxygen. Now let's just connect. Okay. Now, when you look at this, carbon's fine. Well, let me undo this because this is weird. It looks weird because I didn't make it low enough. Oops, that's too thick. Okay, there. Okay, there we go. Now it looks better. All right, so we have 8 around carbon. We know that. We have only 4 around oxygen. Can oxygen have a double bond with hydrogen? No. Can oxygen have a double bond with carbon? No, because then carbon would have more than 4, and carbon doesn't want more than 8. Carbon is not an expanded octet. So the only thing to do is to make 2 more. Now, if we actually did the math like we were supposed to before we started, all right, we would have had 1 carbon, 4 oxygen, 4 hydrogens and 1 oxygen, right? And that would have been a total of 14. All right, let's count. 1, 2, 3, 4, 5, 6, 7. 7 times 2 is 14. So that is the correct Lewis structure. We used every single one and they're in the right place. All right, now let me go to my next one. I need to clear all of these because these are going to be on my stuff and we don't want that. All right, the next one is NO2 negative. Remember, we had this one, since it does have a central atom, we need to do the math. So we got one nitrogen, right? Times 5 gives us 5. We have 2 oxygens times 6 gives us 12. Plus we add 1. So this is a total of 18 valence electrons. Right? We know that the central atom has to be the nitrogen because number 1 is the lowest electronegative, and number 2, there's only 1 of them. So then we place oxygens around it, make the bonds. All right, nobody's happy here, are they? I mean, not a single one of them is happy. So if we do the dots around everybody, right? Okay. How many electrons have we used? Let's see, we have 8 on each one of the oxygens, and then 4 extras on the nitrogen, yes? So that is 16 plus 4 is 20. That means we have too many. So let's go back to the drawing board, all right? So what is something we can do to reduce that number? We can do a double bond. We can erase one of these. Oops, not supposed to be an eraser. All right, let's see. Now let's see if we count. 2, 4, 6, 8, 10, 12, and 6 more is 18. So this is the correct structure. All right, remember it's not correct unless you do this. But is this the only structure that we can have? The answer is no. Remember, we have a resonance structure too. And that resonance structure would be this one. Right? And we have this guy. Now, this is where I think the way that we do it is better. Because if we say 2 bond, remember we had 4, we had 14 left. See, we knew that nitrogen needed 1, you see? Once we did that, and we knew that one of them had to be a double bond, doing it this way. That is why I think that sometimes this is a better way than what she does. Just my opinion. But there you go. Now let's do the other one. And that is C2H4. So we are going to have 2 central atoms, right? And they're both carbons. And then we're going to have 4 hydrogens. So let's just say 1 here, 1 here, 1 here, and 1 here. All right, so let's make the bonds. And let's do the math too. So 2 carbons times 6 is 12. 4 hydrogens times 1 is 4, a total of 16. All right, out of which we've only used 2, 4, 6, 8, right? No, 10, sorry, 10. We've used 10. All right, we still have 6 to use. Carbon's not happy, but hydrogen's happy. Well, obviously. So, but carbon isn't. And it's quite obvious what to do, because if you look, we have just this to do, and everybody has 4 around it. You see that? Now carbon has 4 bonds. And have we used enough electrons? Let's see. 1, 2, 3, 4, 5, 6. Nope, we have not. Did I mess up something? Yes, I did. Ah, Lordy. No wonder the math is not coming on. Oh, man. Sorry, I said 6. I was thinking oxygen. I don't know what I was doing. All right, so 2 times 4. Oops, that's the wrong. Okay. 2 times 4 is 8. And then 4 times 1 is 4. That's a total of 12. Now we have 12, don't we? We have, if you look at it, we have, come on, you. All right, we have 1, 2, 3, 4, 5, 6 times 2 is 12. So we're good. So that's how you do a Lewis structure. You kind of have to use all the electrons that you have in the best possible way, following certain rules. Now, there's something that I didn't show you, and I think this is the coolest thing ever. Now you have, you know, in your periodic table, you have a certain order, right? And you have carbon, then you have, hold on, let me get my periodic table so I'll put it in the right order. All right, so you have carbon, then you have nitrogen, then oxygen, then fluorine. Okay, so you got carbon, nitrogen, oxygen, and fluorine. All right, carbon is in group 4, nitrogen is in group 5, oxygen in 6, and fluorine in 7. If you look at, this is how many bonds these make. Isn't that the coolest? They all add up to 8. So you remember, carbon has 4 electrons, it makes 4 bonds. Nitrogen has 5 electrons, it makes 3 bonds. Oxygen has 6 electrons, it wants to make 2 bonds. Fluorine has 7 electrons, it only wants to make 1 bond. Okay, and that's for every one of those. And it just kind of helps you put things together. You notice how carbon has 1, 2, 3, and 4 bonds, right? See? All right, so let's undo all that mess so we can see the structure. And see, that's exactly what checks here. And if you look at nitrogen, let's see, let's bring this up. Oh, well, okay, so when we did this one, remember nitrogen was like this. See, there's the 3 bonds. Nitrogen likes to make 3 bonds. And of course, you have that lone pair to make its octet. So that was easy. And the oxygen over here, remember, oh, let me do that one. Boom, boom. Okay, right here so we can see it better. Okay, this oxygen right here, right? This oxygen went and did, okay, let me clear this stuff so that I make the point of the oxygen too. And the carbon, see carbon again, making its 4 bonds, right? Oxygen making its 2 bonds. See? So it kind of tells you how to put things together if you look at that. You notice carbon made its 4 bonds, nitrogen made its 3 bonds, and oxygen made its 2 bonds. And of course, fluorine, chlorine, bromine, all of them make 1 bond. So there you go. All right, so we are finished with this. And I want you to look at, and if you look at, actually, before we finish, mouse. Sorry. Okay, so there's your structures, see? And they're all the right one. Of course, this one, he did not do what we're supposed to do, which is your brackets. And he would get a minus from me in his, his one thing that he should have done, which was the person that, like that. That would have been how it should be. And then of course, the last one is the CH4. And there you go. So you can always look at those and check later. All right. And some people do a more formal structure like this one. And basically what you do for this is you'd have to do the formal charge of each one. And we're not doing formal charges right now. So that's why I don't do it that way. All right. So we are pretty much finished for the day. And I will be probably posting this video as soon as it converts, because we were recording, you know that. We always record the lectures. Oh, come on, mouse, get over here. Let's see. Nope, that's not what I meant to do. Okay. This is the one that I need to close off. There we go. All right, so we are done. Bye, Eve. It was nice having you here. And we will see you in class Thursday. All right, bye-bye.